Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe.
James Webb has provided humanity with unprecedented glimpses into the universe, unraveling the mysteries of deep space and revolutionizing our understanding of planets, stars, and galaxies. Its power to peer farther than ever before has led to a series of jaw-dropping discoveries. Among these, perhaps none is more sensational than the claim that the most powerful telescope launched into space has just spotted what appears to be city lights on Proxima b, an exoplanet located just over 424 light-years away from Earth, orbiting in the habitable zone of Proxima Centauri, the closest star to our solar system. This discovery, if verified, would be nothing short of revolutionary, suggesting the existence of artificial structures or civilizations beyond Earth. But how credible is this claim? Could James Webb really detect signs of life, potentially advanced life, on Proxima b? Or are we misinterpreting the data? All this and more will be discussed in today's episode. Discovered in 2016, Proxima b has long captivated scientists because it orbits within the Goldilocks zone, the distance from its star where liquid water could potentially exist on its surface. This proximity to its star makes it an enticing candidate for the search for extraterrestrial life. Proxima b is slightly larger than Earth, with a mass approximately 1.17 times that of our planet. Its star, Proxima Centauri, is a red dwarf, far smaller and cooler than our Sun. But Proxima b's tight orbit means it receives enough warmth to potentially support life. In fact, scientists estimate that it could experience Earth-like temperatures, a crucial factor in the development and sustenance of life as we know it. For years, astronomers have speculated about Proxima b's potential habitability. Could it have an atmosphere? Does it host oceans? Could primitive life or even intelligent life forms have evolved there? These questions took a dramatic turn with recent stunning observations made by James Webb. With its large, segmented mirror and ultra-sensitive instruments, James Webb can detect faint infrared light from distant exoplanets, allowing astronomers to study their atmospheres, temperatures, and surface conditions. It was designed to look for biosignatures, indicators of life such as oxygen, methane, or water vapor, but its precision has led to speculation about whether it might also spot technosignatures, indicators of advanced civilizations such as artificial light or radio signals. As a result, James Webb has already captured the most detailed images of Proxima b yet, peering through the haze of its atmosphere, if it has one, and even analyzing the heat distribution across its surface. But one of the most surprising revelations has come from its observations of Proxima b's night side, the side that is always turned away from its star due to tidal locking, a phenomenon where one side of the planet permanently faces the star while the other remains in perpetual darkness. And here, what James Webb found has sparked intense debate in the scientific community. According to some interpretations of the data, the Webb telescope detected unusual light emissions coming from the night side of Proxima b. These emissions were not consistent with natural phenomena like volcanic activity or auroras, leading some researchers to hypothesize that they could be the result of artificial lighting, similar to the city lights we see on Earth when viewed from space. At first glance, this idea seems far-fetched. How could a space telescope, located millions of miles from Earth, possibly detect something as subtle as city lights on another planet? The answer lies in the unique capabilities of James Webb's infrared sensors, which can detect even faint energy emissions across vast distances. The light observed on Proxima b's dark side reportedly showed a regular grid-like pattern, which would be unusual for any natural process, but highly indicative of structured, artificial sources. If this pattern truly represents city lights, it would mark a transformative shift in humanity's view of its place in the universe. For much of human history, we have assumed that while life elsewhere might exist, intelligent life is either incredibly rare or located at such vast distances that meaningful contact is virtually impossible. But the discovery of an advanced civilization on Proxima b would obliterate this notion. No longer would we speculate in the abstract about intelligent life in distant galaxies. We would know, with certainty, that such life exists right next door in cosmic terms, just over 4 light-years away. This realization would fundamentally reshape humanity's perspective. The discovery of intelligent life on Proxima b wouldn't just answer one of the most profound questions ever posed. Are we alone? It would also raise a cascade of new questions, each more complex than the last. What does this civilization look like? What is their level of technological advancement? Do they know about us? And if so, how do they perceive humanity? Such a revelation would send shockwaves through every field of human endeavor: science, philosophy, politics, and even religion. It would force us to reconsider long-held assumptions about our uniqueness and our place in the grand narrative of life in the cosmos. The discovery would create a sense of both awe and vulnerability, as we grapple with the fact that we are no longer the sole intelligent beings in our corner of the universe. Not only that, but the discovery of city lights on Proxima b also would almost certainly ignite an unprecedented global push to explore and, if possible, contact this extraterrestrial civilization. For centuries, the question of whether we are alone in the universe has fueled both scientific inquiry and speculative fiction. But with hard evidence of intelligent life so close to Earth, the desire to bridge that cosmic gap would become an all-consuming goal. Currently, our space exploration capabilities, though advanced, would take decades to send a spacecraft to Proxima b using existing technology. For example, the fastest spacecraft humans have ever built, Voyager 1, would take over 70,000 years to reach Proxima Centauri at its current speed. However, the discovery of artificial light on Proxima b could serve as a catalyst for accelerating the development of revolutionary technologies that have long been considered theoretical. Concepts like faster-than-light communication or transportation technologies, such as warp drives and wormholes, would likely move from the realm of science fiction into serious scientific study. And the discovery of artificial light on Proxima b would serve as a clarion call to reevaluate these ideas, pushing them from the fringe into the mainstream of scientific research. No longer could we afford to ignore these radical concepts. Humanity would be driven by a collective desire to bridge the gap between us and the civilization on Proxima b, making faster-than-light communication and transportation not just topics of discussion, but necessary goals. Take an example: the concept of a warp drive, a means of traveling faster than light by warping space-time as we know, has long been a favorite in science fiction. Popularized by franchises like Star Trek, warp drives seem fantastical, but recent scientific studies, including those by NASA physicist Harold White, have shown that the physics of a warp drive may not be entirely impossible. In theoretical terms, a warp drive would involve creating a bubble of space-time around a spacecraft, contracting the space in front of the vessel while expanding the space behind it. This would allow the craft to ride the wave of warped space, effectively enabling faster-than-light travel without violating the laws of physics, as the ship itself wouldn't be moving faster than light within its local space. If we detect artificial light on Proxima b, the pressure to develop this technology would skyrocket. No longer would warp drives be relegated to speculative science fiction. Instead, it would become an urgent scientific objective. The potential rewards are obvious: a means of reaching Proxima b in a reasonable amount of time. Currently, with conventional propulsion methods, it would take over 4.2 years to reach Proxima b at the speed of light, assuming we could even achieve that. With a warp drive, that journey could be shortened dramatically, allowing us to make first contact in a matter of years rather than centuries. Another theoretical technology that could become a central focus after the discovery of artificial light on Proxima b is the concept of wormholes. Wormholes are hypothetical passages through space-time that could, in theory, connect two distant points in the universe, allowing for instantaneous travel. While the idea of a wormhole has been a staple of science fiction, it also has roots in general relativity. Albert Einstein and physicist Nathan Rosen first proposed the idea of what they called bridges in space-time, which have come to be known as Einstein-Rosen bridges, or wormholes. Like warp drives, the study of wormholes has remained mostly academic, with few real-world applications explored. However, the urgency of reaching Proxima b could shift research priorities. If an advanced civilization exists on Proxima b, it's possible they have already mastered such a technology. Understanding how they achieved this could inspire breakthroughs in our own understanding of physics, allowing us to create stable, traversable wormholes. The discovery of artificial light on Proxima b would likely spark a new age of space exploration, one that places wormholes at the forefront of scientific research. If successful, wormholes could allow for near-instantaneous travel between Earth and Proxima b, effectively making interstellar travel a reality and reshaping humanity's role in the universe. In addition to the desire for faster-than-light travel, there would be a parallel push for faster-than-light communication. Given that Proxima b is located 4.24 light-years away from Earth, any messages sent using conventional radio waves would take over 4 years to reach the planet, with an additional 4 years to receive a reply. This time delay would make meaningful communication almost impossible, especially if we were attempting to coordinate collaborative projects or diplomatic efforts. Quantum entanglement, a phenomenon in which two particles become linked such that the state of one instantly affects the state of the other, even across vast distances, could be the key to overcoming this challenge. While the use of quantum entanglement for faster-than-light communication has been debated, some physicists believe it may hold the potential to send information instantaneously, regardless of the distance between the two particles. Should artificial light be discovered on Proxima b, the need for faster communication would intensify research into quantum communication technologies. This could lead to breakthroughs in quantum mechanics that allow for the development of a reliable, faster-than-light communication network. Such a system could fundamentally change the way we interact, not only with extraterrestrial civilizations, but also with distant human colonies in the future. The discovery of artificial light on Proxima b would also spark unprecedented levels of global cooperation and innovation. Much like the space race during the Cold War, this event could lead to a new era of scientific rivalry, but with a more collaborative twist. The stakes would be far greater, pushing world governments, private corporations, and international institutions to work together in ways previously unimaginable. International collaborations akin to the European Organization for Nuclear Research, also known as CERN, or the International Space Station could form, dedicated to the research and development of faster-than-light travel and communication technologies. New research institutes could arise, combining the world's brightest minds to tackle the complex challenges of reaching and communicating with Proxima b's civilization. Private companies would also play a significant role in this technological revolution. Much like SpaceX has revolutionized the space industry with reusable rockets, a discovery of artificial light on Proxima b could inspire new ventures focused on deep space exploration, propulsion technologies, and even colonization of distant planets. Beyond technological innovations, the discovery about Proxima also would trigger an explosion of scientific exploration. Every aspect of life on Proxima b would be subject to intense scrutiny. How did life develop there? Does it follow the same biochemical rules as life on Earth? Or is it based on entirely different principles? And perhaps most crucially, how did this civilization manage to survive the challenges of technological development? Have they overcome the existential risks that we currently face on Earth, such as nuclear war, climate change, or artificial intelligence? The answers to these questions could offer valuable insights into the future of humanity. If the civilization on Proxima b has successfully navigated the perils of technological advancement, they may possess knowledge that could help humanity solve its own problems. On the other hand, if they have struggled with these challenges, or worse, if they are a civilization in decline, then their experience could serve as a cautionary tale for humanity. Beyond the technological and scientific realms, the discovery of city lights on Proxima b would spark a profound philosophical and ethical debate. For centuries, thinkers have speculated about the existence of extraterrestrial life, but these speculations have always been theoretical. With concrete evidence of intelligent life, the ethical questions surrounding contact with another civilization would move to the forefront. One of the first ethical questions would be whether we should attempt to contact the civilization on Proxima b. While the discovery of city lights might indicate technological sophistication, we would have no way of knowing whether this civilization is friendly or hostile. Could making contact with them put humanity at risk? Some scientists have warned that broadcasting our existence to the cosmos could be dangerous, citing historical examples of what happens when a more technologically advanced society encounters a less advanced one, such as the European colonization of the Americas, which led to the decimation of indigenous populations. On the other hand, refusing to attempt contact could represent a missed opportunity to learn from another intelligent species. The benefits of communication could be enormous, particularly if the Proxima b civilization is more advanced than we are. They might possess technologies that could solve many of the problems facing humanity, from renewable energy sources to cures for diseases. They could also offer insights into the ethical and social challenges that come with advanced technology, providing a glimpse of humanity's potential future. The discovery would also raise questions about the nature of intelligence and consciousness. What does it mean to be an intelligent species? Is intelligence an inevitable outcome of evolution, or is it a rare and unique phenomenon? If life on Proxima b developed independently from life on Earth, it could provide a test case for some of the most fundamental theories in biology, psychology, and even artificial intelligence. While the discovery of city lights on Proxima b would undoubtedly represent a monumental achievement for science, it would also come with significant risks. The most immediate concern would be the possibility of misinterpreting the signals. What if the lights aren't actually artificial at all, but rather the result of some natural phenomenon that we don't yet understand? Jumping to conclusions could lead to embarrassment or worse, wasted resources on misguided attempts to communicate with a civilization that doesn't exist. Even if the lights are artificial, the risks of contacting an extraterrestrial civilization are immense. We have no way of knowing whether the inhabitants of Proxima b are peaceful or hostile. History provides numerous examples of how encounters between different civilizations can go disastrously wrong. The risk of inadvertently provoking a conflict with an extraterrestrial society is real, and it would require careful consideration before any attempt at contact is made. However, as told, the discovery would bring with it significant risks. The potential rewards, in terms of knowledge, technological advancement, and even global unity, are immense. If the lights on Proxima b truly represent the existence of an advanced civilization, then humanity is on the cusp of a new era of exploration and discovery, one that could forever change the course of our species. And while Proxima b remains an exciting discovery due to its proximity to Earth and its possible host for life, many scientists believe that other exoplanets might be even better candidates for harboring extraterrestrial life. Here are some. Number 1. TRAPPIST. 1. A complex, rocky world in the habitable zone. TRAPPIST-1e is part of the fascinating TRAPPIST-1 system, located about 40 light-years away from Earth. The system contains 7 Earth-sized planets, 3 of which are located in the habitable zone, the region around a star where conditions may be just right for liquid water to exist. Among these, TRAPPIST-1e stands out due to its size, density, and the possibility of having a stable atmosphere. One of the main reasons why TRAPPIST-1e is considered a strong candidate for hosting life is its parent star, a relatively cool red dwarf. Unlike Proxima Centauri, TRAPPIST-1 is a much quieter star, which reduces the likelihood of intense stellar flares that could strip the atmosphere or expose the surface of the planet to harmful radiation. This increases the chances of TRAPPIST-1e maintaining a stable environment where life could develop and thrive. The planet's Earth-like density also suggests that it has a rocky composition, which is essential for the presence of solid surfaces and oceans, crucial elements for the potential development of life as we know it. Observations from the James Webb Space Telescope and other instruments could soon give us more details about its atmospheric composition, potentially detecting water vapor, oxygen, or other biosignatures. Number 2. LHS 1140b, a super-Earth in a super-habitable zone. LHS 1140b is located about 40 light-years away from Earth in the constellation Cetus. This planet is considered a super-Earth due to its size, which is larger than Earth but smaller than gas giants like Neptune. Its mass and density suggest a rocky composition similar to Earth, which makes it an intriguing candidate for hosting life. One of the most exciting aspects of LHS 1140b is its location within the habitable zone of its star, a red dwarf. What sets this planet apart is its potential for retaining a thick atmosphere, which would protect any life from harmful radiation. Additionally, its relatively high gravity could help it retain water vapor and other vital gases over long periods, enhancing its potential for habitability. The planet also experiences less intense stellar activity compared to Proxima b's star, which suggests that its surface may be more stable and less prone to being scorched by radiation. LHS 1140b's thick atmosphere could also support complex weather patterns, oceans, and potentially microbial life. Recent studies using the Hubble Space Telescope have suggested that LHS 1140b may have had a liquid water ocean in its past, and it may still retain water in its atmosphere. The planet's stable climate and rocky composition make it an excellent candidate for further exploration with future telescopes. Number 3. Kepler 442b, a far-flung yet promising world. Kepler 442b is a rocky exoplanet located about 2,200 light-years away from Earth in the constellation Lyra. Despite its distance, it is one of the most Earth-like exoplanets discovered, with a size only slightly larger than our home planet and an orbit in its star's habitable zone. This makes Kepler 442b a tantalizing target for scientists searching for life. Kepler 442b orbits a K-type star, which is cooler and more stable than a G-type star like our Sun. This means the planet could enjoy a longer and more stable period of habitability. While Proxima b's star is prone to extreme flaring events that could render its surface hostile to life, Kepler 442b's host star offers a more placid environment where life could thrive over billions of years. Additionally, because of its size and distance from its parent star, Kepler 442b likely possesses a thick atmosphere, which could help moderate its climate and make it conducive to liquid water. Scientists hypothesize that the planet's orbit would allow it to receive just the right amount of stellar energy to maintain liquid water, a crucial factor for life. While much of the research into Kepler 442b is still speculative due to its distance, it remains one of the most promising exoplanets in the search for alien life. Number 4. Teegarden b, a nearby Earth-like planet. Discovered in 2019, Teegarden b is one of the closest known Earth-like exoplanets, located just 12 light-years away from us. The planet orbits an ultra-cool red dwarf star and is part of a system with at least 2 planets. Teegarden b is situated in the habitable zone of its star, making it a prime candidate for the presence of liquid water and life. What makes Teegarden B particularly exciting is its Earth-like temperature and conditions. If it has an atmosphere similar to Earth's, the planet could potentially support a stable climate conducive to the development of life. Its relatively close distance from Earth makes it a more accessible target for future missions that aim to directly image and study exoplanets. Teegarden B's star is also more stable than Proxima Centauri, reducing the likelihood of damaging stellar flares. This, combined with the planet's size and position in the habitable zone, makes it one of the most promising nearby exoplanets for future research. Furthermore, Teegarden B's star is ancient, giving the planet billions of years of potential stability, during which life could have emerged. Although we still lack detailed information about its atmosphere and surface conditions, upcoming missions could provide more insights into this nearby Earth-like world. Number 5. Europa, a moon with hidden oceans. While not an exoplanet, Europa, one of Jupiter's moons, remains one of the most intriguing candidates for life within our solar system. Unlike Proxima b, Europa is not located in a traditional habitable zone. However, beneath its icy surface lies a vast ocean, potentially containing more water than all of Earth's oceans combined. The presence of liquid water, along with the possibility of hydrothermal vents on the ocean floor, makes Europa one of the most promising places in our solar system for the search for extraterrestrial life. These hydrothermal vents could provide the necessary heat and chemical energy to support life, much like similar environments on Earth do for extremophiles, organisms that thrive in extreme conditions. NASA's upcoming Europa Clipper mission is set to explore this intriguing moon further, analyzing its ice shell and subsurface ocean for signs of habitability. While Europa is not an exoplanet like Proxima b, its proximity and potential for life make it a key target in the search for extraterrestrial biology. In short, these worlds represent some of the most exciting places to search for life beyond Earth. With advances in telescopes and space exploration missions, we may soon have the tools to determine whether any of these distant worlds are home to alien life. In the meantime, a brand new observatory has just revealed a planetary system anchored by a dead white dwarf star, located around 4,000 light-years away, has offered astronomers a possible glimpse into what our Sun and Earth could look like in around 8 billion years. However, this would only be Earth's future if our planet manages to survive the Sun's eventual transformation into a swollen red giant. This transformation is expected to happen around 5 billion to 6 billion years from now, when the Sun finally exhausts its fuel supply needed for nuclear fusion. That red giant phase will see the Sun swell up to around the orbit of Mars, swallowing Mercury, Venus, and maybe Earth, too. After this, the Sun would become a smoldering white dwarf, just like the one seen in the observed planetary system. One way our planet could escape destruction by the red giant Sun is if it migrates out to the orbit of Mars or beyond. This would leave our planet a radiation-blasted, yet freezing husk, orbiting a burned-out star. This new planetary system offers evidence that such a miracle escape is possible. The team identified a white dwarf with around half the mass of the Sun and an Earth-sized companion planet in an orbit twice as wide as our planets around our star, offering a picture of what a surviving Earth could look like in around 8 billion years. One element of the system, located near the central bulge of the Milky Way galaxy, sets it apart from the future solar system. Another occupant with a mass around 17 times that of Jupiter, the solar system's most massive planet. This object is likely to be a brown dwarf, a body often referred to as a failed star, because it forms like a star, but fails to pile on the mass needed to trigger the fusion of hydrogen to helium in its core, the nuclear process that defines a main-sequence star like the Sun. Astronomers discovered this analog for the future of the solar system when they observed a so-called microlensing event, referring to the curvature of light from a background source caused by the gravitational influence of a body passing between that source and Earth. The particular event was caught using the Korea Micro-Lensing Telescope Network in the Southern Hemisphere. Microlensing is a weak form of gravitational lensing, a phenomenon first predicted by Albert Einstein with his general relativity theory. General relativity suggests that objects with mass cause the very fabric of space-time, a four-dimensional unification of space and time, to warp. Not only does gravity arise from this warping, but the warps also bend light when waves from a background source passes through them. This bent light then appears brightened from our perspective because of the curved path it is forced to take on its way to our detectors. This event, dubbed KMT 2020 BLG 0414, was observed in 2020. It consisted of the brightening of a background star, located 24,000 light-years away, by around 1,000 times. The objects or lenses causing this brightening are the bodies of the planetary system. To investigate this planetary system further, the University of California, Berkeley, team led by Kaming Zhang and Eric and Wendy Schmidt, AI in Science postdoctoral, fellow at the University of California, followed up the microlensing event with the Keck 10-meter telescopes in Hawaii. The initial investigation didn't reveal the nature of the central star. It took the researchers another 3 years of study using the Keck telescopes to determine that this stellar body is an exhausted white dwarf. This wasn't evident from what the team saw, but rather from what they didn't see. Images of the system failed to show the light that would be expected from a main sequence star. Continuing the investigation of this system also allowed the team to resolve the orbit of the brown dwarf and relieve confusion surrounding the failed star's position around the dead star, as well as the fact that it isn't simply a very close-in massive planet or hot Jupiter. While this planetary system serves as evidence that Earth could escape consumption by the Sun in around 6 billion years, it doesn't tell us if any life on our planet, if it still exists by then, could also survive. It does seem that if the loss of the Sun's grip on Earth during the red giant phase allows it to escape our star's swelling outer layers, this migration would also put it outside the habitable zone. The habitable zone, or Goldilocks zone, is defined as the region around a star with temperatures neither too hot nor too cold to allow a planet to hang onto liquid water, a crucial ingredient for life. However, humanity's time on Earth is likely to have run out around 4 billion to 5 billion years before the Sun goes red giant. That means humanity could migrate outward into the solar system to avoid this fate. Potential targets for resettlement could be the moons of Jupiter, such as Europa, Callisto, and Ganymede, or Enceladus, which orbits Saturn. These moons appear to have frozen water oceans that, though icy now, could ironically be made habitable by the expanding Sun. That's because the Sun could potentially thaw them, making them ocean worlds. The team suggests that this research demonstrates the potential of microlensing as a technique to investigate planetary systems and their stars. One instrument that could fully take advantage of this is the forthcoming Nancy Grace Roman telescope, scheduled for launch in 2027. NASA's next major space telescope will use microlensing to hunt for extrasolar planets or exoplanets. Located just 4.24 light-years from Earth, Proxima b represents one of the most exciting prospects for finding life beyond our solar system. This exoplanet orbits within the habitable zone of its parent star, raising the tantalizing possibility that it could host conditions favorable for life. However, while the promise of Proxima b is immense, numerous challenges complicate our understanding of this distant world. But now, with the addition of the James Webb Space Telescope, a technological marvel that has pushed the boundaries of astronomical observation, we have just achieved a groundbreaking feat: the clearest image of Proxima b ever seen. And that could change everything we think we know about our closest exoplanet neighbor. Join us as we dig deep into the most intriguing revelations of Proxima b and what they might reveal about the potential for life beyond. Let's start with an overview of Proxima b. This world was discovered by astronomers using the radial velocity method, which detects the slight wobble of a star caused by the gravitational pull of an orbiting planet. This method provided strong evidence for the existence of a planet about 1.17 times the mass of Earth, orbiting Proxima Centauri every 11 days. This close proximity to its parent star places Proxima b within the so-called habitable zone, the region around a star where liquid water could exist on a planet's surface. Given that water is a key ingredient for life as we know it, the planet's location immediately sparked excitement about its potential to host life. Proxima b's discovery was especially significant because Proxima Centauri is the closest known star to the Sun, making its planetary system one of the most accessible in terms of future space exploration. This proximity has opened up possibilities for more detailed study and has led to bold proposals for missions to send probes to the Proxima system in the coming decades. Despite its closeness, Proxima b remains a deeply mysterious world. Classified as a red dwarf star, Proxima Centauri is significantly smaller and cooler than our Sun. And while red dwarfs are the most common type of star in the galaxy, they present unique challenges for planets that orbit them. One of the most intriguing aspects of Proxima b's mystery lies in the nature of its star. Proxima Centauri is known to be highly active, emitting frequent and intense stellar flares that could have profound effects on Proxima b. These flares, composed of radiation and charged particles, might strip away a planet's atmosphere over time, rendering it inhospitable. For Proxima b, which orbits just 0.05 astronomical units from its star, about 1/20th the distance between Earth and the Sun, the threat from such flares is a serious concern. The planet is likely tidally locked, meaning one side always faces the star while the other remains in perpetual darkness, creating extreme temperature differences. This leads to one of the major questions surrounding Proxima b. Can it sustain an atmosphere under such harsh stellar conditions? If Proxima b has lost its atmosphere, it would likely be a barren, lifeless world. However, some models suggest that it could retain a thick enough atmosphere to protect the surface from radiation. Alternatively, if Proxima b has a magnetic field similar to Earth's, it could shield the planet from these harmful effects. Determining whether Proxima b has an atmosphere and, if so, what it consists of, is one of the most pressing challenges for astronomers. Proxima b's location in the habitable zone suggests that liquid water might exist on its surface, but the conditions required for habitability are far more complex than simple proximity to a star. The intense stellar activity of Proxima Centauri, combined with the possibility of tidal locking, complicates the question of habitability. In the tidally locked scenario, one side of Proxima b would be bathed in constant daylight, while the other would be trapped in eternal night. The terminator line, the boundary between the day and night sides, might be a region where temperatures are moderate enough for water to exist in liquid form. This strip of twilight could potentially support life, but much depends on the planet's atmospheric dynamics. If the atmosphere is capable of redistributing heat from the day side to the night side, it might create a more temperate climate overall. However, if the atmosphere is thin or non-existent, the surface could be frozen on one side and scorched on the other. The composition of Proxima b's surface is another enigma. Is the planet rocky, like Earth, or is it covered in oceans or ice? Spectroscopic studies using powerful telescopes like the James Webb Space Telescope could eventually provide clues about the planet's composition, but as of now, scientists can only speculate. Some models suggest that Proxima b could have a significant amount of water, possibly as much as several Earth oceans, but this remains unconfirmed. Even if Proxima b has the right conditions for life, detecting signs of life from Earth presents significant challenges. Direct imaging of the planet is difficult due to its proximity to Proxima Centauri and the faintness of the light it reflects. Instead, Astronomers rely on indirect methods, such as studying the planet's atmosphere for biosignatures, chemical markers like oxygen, methane, or other compounds that might indicate the presence of life. The James Webb Space Telescope plays a crucial role in these efforts. As the most powerful space observatory ever built, James Webb represents a leap forward in space exploration technology. Equipped with a massive 6.5-meter primary mirror and 4 sophisticated instruments, the telescope is capable of capturing the most distant and faint objects in the universe. Its infrared vision allows it to peer through cosmic dust and gas, revealing stars, galaxies, and planets with exceptional clarity. For Proxima b, James Webb's infrared capabilities are particularly crucial. Proxima Centauri is a red dwarf star, which emits most of its energy in the infrared spectrum. Proxima b, orbiting close to this star, is subject to these infrared emissions, making it an ideal candidate for Webb observations. Unlike previous telescopes that relied on visible light, James Webb can examine the heat signatures of Proxima b, providing new insights about this intriguing world. One of Webb's primary objectives in studying Proxima b is to analyze its atmosphere. Determining whether Proxima b has a thick, stable atmosphere is critical for understanding its potential to support life. Red dwarf stars like Proxima Centauri are notorious for emitting strong solar flares and ultraviolet radiation, which can strip a planet's atmosphere over time. If Proxima b has managed to hold on to its atmosphere, it would be an extraordinary discovery, indicating that planets around red dwarfs might be more resilient than previously thought. James Webb employs a technique known as transmission spectroscopy to investigate Proxima b's atmosphere. As the planet passes in front of its star, light from Proxima Centauri filters through the planet's atmosphere, allowing scientists to analyze the different wavelengths absorbed by various gases. By examining the light spectrum, James Webb can identify the presence of molecules like carbon dioxide, methane, and even water vapor, which are key indicators of habitability. The telescope's infrared capabilities are particularly advantageous for this task. Previous missions, such as the Hubble Space Telescope, were limited in their ability to detect atmospheric compositions due to their reliance on visible and ultraviolet light. James Webb, with its focus on infrared, can detect the thermal signatures of gases even in cooler atmospheres like that of Proxima b. The ultimate goal in studying exoplanets like Proxima b is to search for signs of life. While discovering an atmosphere would be a significant achievement, the detection of biosignatures, gases, or chemical compounds that suggest biological activity would be even more profound. James Webb is equipped to look for gases like oxygen, ozone, and methane, which could indicate the presence of life. Oxygen is a particularly strong biosignature, as it is typically produced by photosynthetic organisms. If the telescope detects oxygen in Proxima b's atmosphere, it would suggest that life, at least in some form, could exist on the planet. Methane is another important biosignature. While methane can be produced by geological processes, it is also a byproduct of biological activity on Earth. The simultaneous detection of methane and oxygen would provide compelling evidence for life. Moreover, Webb's ability to detect water vapor is critical for assessing Proxima b's habitability. Water is a fundamental requirement for life as we know it, and its presence in Proxima b's atmosphere or on its surface would increase the likelihood that the planet could support life. Webb's instruments are sensitive enough to detect even small amounts of water vapor, making it a powerful tool in the search for habitable worlds. While atmospheric composition is essential for determining Proxima b's habitability, understanding its surface conditions is equally important. The Webb telescope aims to provide insight into whether Proxima b's surface resembles that of Earth or if it is more hostile. Factors such as surface temperature, atmospheric pressure, and the presence of liquid water are all critical in assessing Proxima b's potential for hosting life. As told, Proxima b is tidally locked, meaning that one side of the planet always faces its star, while the other side is in perpetual darkness. This could lead to extreme temperature differences between the two hemispheres. The side facing Proxima Centauri may be scorching hot, while the dark side could be frigid. However, if Proxima b has a thick atmosphere, it could help distribute heat more evenly across the planet, potentially creating more stable conditions conducive to life. James Webb will measure the planet's heat signature using its mid-infrared instrument, or known as MIRI, which is capable of detecting thermal radiation emitted by Proxima b. By studying the planet's temperature distribution, James Webb can provide clues about the composition and thickness of its atmosphere, as well as the possibility of liquid water on the surface. Studying Proxima b is not only important for understanding this particular exoplanet, but also for gaining insight into the broader context of planetary systems around red dwarf stars. Red dwarfs make up about 70% of the stars in the Milky Way, and many of them are known to host planets. If James Webb finds that Proxima b is potentially habitable, it could suggest that habitable planets around red dwarfs are more common than previously thought. On the other hand, if Proxima b is found to be uninhabitable due to the harsh conditions imposed by its parent star, it would reinforce the idea that planets around red dwarfs face significant challenges in retaining their atmospheres. In either case, Webb's observations will provide valuable data that can be applied to other exoplanetary systems, helping scientists refine their models of planetary habitability. In short, the James Webb Space Telescope's exploration of Proxima b represents a new chapter in the study of exoplanets. With its advanced capabilities, James Webb is poised to provide unprecedented insight into the atmosphere, surface conditions, and potential for life on Proxima b. While many questions remain unanswered, the tantalizing possibility that it could harbor life or provide a secondary home for humanity has driven interest in developing the means to reach it. However, let's first accept that while 4 light-years may seem close compared to the vastness of space, it is an almost unimaginable distance in practical terms. Current human-made spacecraft, like the Voyager probes, travel at speeds of around 17 kilometers per second. At that speed, it would take over 70,000 years to reach Proxima b. Clearly, we need a radically new approach to interstellar travel. To make the journey within a human lifetime, the spacecraft must travel at a significant fraction of the speed of light. Achieving this will require technological breakthroughs in propulsion, energy generation, and spacecraft design, all of which are currently in their infancy. One of the major barriers to interstellar travel is the lack of a feasible propulsion system. Traditional rocket propulsion, which relies on chemical reactions, is insufficient for the vast distances involved in a journey to Proxima b. New propulsion systems will be needed, and several promising concepts have been proposed. 1. Nuclear propulsion. Nuclear propulsion, both fission and fusion-based, could offer a way to achieve higher speeds than chemical rockets. In a nuclear fission system, atoms of uranium or plutonium are split, releasing energy that could be used to propel a spacecraft. Theoretically, nuclear propulsion could achieve speeds up to 10% of the speed of light, making the trip to Proxima b in about 40 years. Fusion propulsion, which mimics the process that powers the sun, offers even greater potential. In a fusion reaction, atoms of hydrogen are fused together to create helium, releasing vast amounts of energy. While the technology to build a working fusion engine does not yet exist, it holds the promise of higher efficiency and faster speeds than fission, potentially reaching 20% of the speed of light. This would reduce the travel time to around 20 years. 2. Laser-powered light sails. Another innovative concept is the use of light sails powered by laser beams. This idea is central to the breakthrough Starshot project, an initiative proposed by billionaire Yuri Milner and supported by scientists such as Stephen Hawking. The project envisions tiny, lightweight spacecraft equipped with reflective sails that could be propelled by powerful lasers fired from Earth or from space-based stations. These laser-powered sails could, in theory, accelerate the spacecraft to around 20% of the speed of light, allowing them to reach Proxima b in just over 20 years. The key advantage of this system is that the spacecraft does not need to carry its own fuel, significantly reducing its mass. However, the engineering challenges are immense, including the need for an array of lasers powerful enough to propel the spacecraft and the difficulty of steering the light sail across vast distances. 3. Antimatter propulsion. Antimatter propulsion, while still highly speculative, offers the most efficient means of space travel known. When matter and antimatter collide, they annihilate each other, releasing 100% of their energy. In comparison, nuclear fission and fusion release only a tiny fraction of the energy locked within atoms. An antimatter-powered spacecraft could theoretically travel at speeds approaching the speed of light, making the trip to Proxima b in under a decade. However, producing and storing antimatter in the quantities needed for space travel is far beyond current capabilities. The energy required to create even a tiny amount of antimatter is astronomical, and the cost of producing just a few grams would bankrupt any nation. However, even if we solve the propulsion problem, there are enormous challenges associated with sending humans on such a long journey. The voyage to Proxima b would likely take decades, even with the most advanced propulsion systems. This raises several key concerns. 1. Human lifespan and aging. If a mission to Proxima b takes decades, we must address the problem of human aging and lifespan. One option is to send multiple generations of humans on a generation ship, where the original crew's descendants would complete the journey. However, this raises social and ethical questions about the nature of life on a spaceship, where entire generations would be born, live, and die without ever setting foot on Earth or the destination planet. Another possibility is cryogenic suspension, freezing the crew members for the duration of the journey and then reviving them upon arrival. While this technology is far from mature, research in cryopreservation is ongoing, particularly in the field of medicine. Achieving reliable and safe cryogenic sleep for humans would be a major breakthrough for interstellar travel. 2. Radiation and space environment. Space is a hostile environment. Beyond the protection of Earth's magnetic field, astronauts would be exposed to dangerous levels of cosmic radiation, which can cause cancer and other health issues. A journey to Proxima b would require advanced shielding technologies to protect the crew from this radiation. Additionally, the spacecraft would need to be completely self-sustaining, as resupply missions would be impossible. This means it would need to generate its own oxygen, food, and water for the duration of the trip. Closed-loop life support systems, which recycle waste into usable resources, will be essential. NASA is already developing such systems for long-term missions to Mars, but they would need to be scaled up and perfected for an interstellar journey. 3. Psychological and social issues. The isolation and confinement of space travel can have severe psychological effects. On a journey lasting decades, maintaining the mental health of the crew will be a significant challenge. Space travelers would be cut off from the rest of humanity, and the stress of living in close quarters with the same people for years could lead to interpersonal conflicts. Ensuring the well-being of the crew will require careful selection of personnel, comprehensive psychological support, and perhaps even virtual reality systems to simulate a more varied environment. Alternatively, robotic or artificial intelligence, also known as AI, crew members, could be used to minimize the psychological burden on human travelers. Given the dangers and challenges of sending humans to Proxima b, some have proposed that the first missions should be conducted by robotic probes. Advances in AI and robotics could allow for autonomous spacecraft capable of conducting scientific research, scouting the planet for potential habitability, and sending data back to Earth. A robotic mission could pave the way for human exploration, providing vital information about Proxima B's atmosphere, geology, and potential for life. These probes could also set up infrastructure, such as automated habitats or resource extraction systems that humans could later use when they arrive. Beyond the practical challenges of interstellar travel, there are more speculative ideas that could one day revolutionize our ability to traverse the stars. Warp drives and wormholes are concepts rooted in the theories of general relativity and quantum mechanics. While currently the stuff of science fiction, they represent potential shortcuts through space. Warp drives, first made famous by science fiction like Star Trek, propose a method of FTL for faster-than-light travel that doesn't violate the laws of physics. In 1994, theoretical physicist Miguel Alcubierre developed a model for a warp drive based on Einstein's equations. The Alcubierre drive proposes creating a bubble of space-time around a spaceship, contracting space-time in front of the ship while expanding it behind. This bubble would effectively move the spaceship faster than light without the craft itself exceeding the speed of light, a key requirement, since nothing can move faster than light within space-time according to Einstein's special relativity. The idea of the warp drive hinges on the concept of space-time manipulation. Space-time, according to Einstein's general theory of relativity, is malleable and can be stretched or contracted by mass and energy. In theory, by creating a region of contracted space in front of a spacecraft and an expanded region behind it, the craft could ride this wave and traverse vast distances at superluminal speeds without violating any physical laws. Essentially, the spacecraft would remain stationary within its bubble while the space around it moves. The Alcubierre drive is a speculative concept, and its practicality faces several monumental challenges. One issue is the enormous amounts of energy required. Early estimates suggested that the amount of energy needed to create a warp bubble would be equivalent to the mass energy of an entire planet. However, some later studies have refined these calculations, suggesting that the energy requirements might be reduced if we use exotic matter, a theoretical substance that has negative energy density. Though the warp drive remains theoretical, there have been advances in understanding the mathematics and physics behind it. In 2021, a group of researchers claimed to have found a new solution to the Alcubierre metric that significantly reduced the energy requirements, bringing the idea closer to feasibility. This research suggests that the warp drive might be achievable without violating known physical laws, but it would still require exotic materials and advanced technology far beyond our current capabilities. Another problem with the warp drive is how to generate and control the warp bubble. This would involve manipulating space-time itself, something that, as of now, we have no practical means to accomplish. Additionally, the presence of exotic matter, which has not yet been discovered, is crucial for maintaining the negative energy densities required for the warp bubble. Despite these challenges, the possibility of FTL travel using a warp drive is a tantalizing concept that continues to inspire researchers. Another promising concept for revolutionizing space travel is the idea of wormholes. A wormhole, also called an Einstein-Rosen bridge, is a hypothetical tunnel through space-time that connects two distant points. Wormholes would allow a spacecraft to travel enormous distances in a short amount of time by passing through a shortcut in space-time. Like warp drives, the idea of wormholes comes from Einstein's theory of general relativity. In 1935, Einstein and physicist Nathan Rosen used the equations of general relativity to propose the existence of bridges through space-time, wormholes. These wormholes could, theoretically, connect two distant locations in the universe, enabling instantaneous travel between them. The most well-known type of wormhole in theoretical physics is the traversable wormhole, first described by physicist Kip Thorne in the 1980s. A traversable wormhole would allow for safe passage from one end to the other, unlike many of the other solutions that lead to singularities or collapse too quickly to be useful. One of the main challenges in creating a wormhole is that it would require exotic matter with negative energy to keep it open. Like the warp drive, the existence of such exotic matter has not been confirmed. Without negative energy, a wormhole would collapse on itself before anything could pass through. This negative energy requirement is a significant hurdle, but it doesn't render the idea of wormholes impossible. In fact, quantum field theory allows for the existence of negative energy in small quantities, as seen in the Casimir effect, which raises the possibility that future advances in quantum physics could provide a way to stabilize wormholes. If wormholes can be created and stabilized, they could enable instantaneous travel between distant points in space. For example, a wormhole connecting our solar system with another galaxy would allow for immediate travel across vast distances that would otherwise take millions of years using conventional propulsion systems. Wormholes also raise intriguing possibilities for time travel. Since wormholes link 2 points in space-time, they could, in theory, be used to travel through time as well as space. This has led to some speculative theories about using wormholes as time machines, though the physics of time travel is even more speculative and fraught with paradoxes. In short, traveling to Proxima b is an extraordinary challenge, but it is not beyond the realm of possibility. With advancements in propulsion technology, human biology, and spacecraft design, the dream of interstellar travel could become a reality within the next few centuries. Although the technical and logistical obstacles are daunting, the desire to explore and expand beyond our solar system is a powerful motivator. As we stand on the threshold of becoming an interstellar species, Proxima b serves as both a destination and a symbol of humanity's enduring quest for knowledge and exploration. One day, perhaps, we will look back on this time as the moment we first began our journey to the stars. And what's notable, besides Proxima b, there are also other notable potential homes beyond Earth. And here is a quick look at the most promising exoplanets that scientists believe could harbor life or offer clues to the formation of planetary systems. The TRAPPIST-1 system, located 39 light-years away in the constellation Aquarius, has become a focal point in the search for habitable worlds. It consists of 7 rocky planets, 3 of which, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, are located in the star's habitable zone. What makes this system especially remarkable is that all 7 planets are roughly the size of Earth, and are in such close proximity to one another that an observer on one planet could likely see the others in the sky. The TRAPPIST-1 star is a red dwarf, much cooler and dimmer than our Sun, allowing the planets to orbit much closer to the star without experiencing extreme heat. This compact arrangement also means that studying the system is easier. Scientists can observe how the planets interact gravitationally, giving insights into their masses and compositions. TRAPPIST-1e, in particular, has emerged as a standout candidate for habitability. Its location in the middle of the habitable zone means it might have liquid water on its surface. Moreover, it is dense enough to suggest a rocky composition similar to Earth's. While the system's planets likely experience tidal locking, there's potential that atmospheric circulation could distribute heat, making parts of the planets temperate and potentially habitable. Elsewhere, LHS 1140b is also a top candidate. Discovered in 2017, LHS 1140b is a super-Earth orbiting a red dwarf star about 49 light-years from Earth. This rocky planet is about 1.4 times the size of Earth, but has 6 times our planet's mass, suggesting it is exceptionally dense. LHS 1140b orbits its star at just the right distance to lie within the habitable zone, making it a promising candidate for habitability. What sets LHS 1140b apart is its atmosphere. Scientists have detected a potentially thick atmosphere that may protect the planet from harmful radiation and maintain surface temperatures that could support liquid water. Given its mass and size, the planet's gravity could help it retain this atmosphere even under the bombardment of radiation from its star. This exoplanet's relatively short distance from Earth and the presence of a dense atmosphere make it a target for further exploration, particularly with instruments like James Webb, which can analyze its atmospheric composition in detail. If it harbors signs of water vapor or even biosignatures like oxygen, it could be one of the most exciting discoveries in exoplanet science. Kepler 452b, discovered by NASA's Kepler mission, has been dubbed Earth's cousin because of its size and location in the habitable zone of a sun-like star. Located 1,400 light-years away, Kepler 452b is about 60% larger than Earth and orbits a G-type star similar to our Sun, although it is slightly older. The age of Kepler 452b's star, estimated to be 6 billion years, raises fascinating questions about the planet's evolutionary path. If Kepler 452b had conditions conducive to life in its past, it may have supported life for billions of years, giving it a significant evolutionary head start compared to Earth. However, its older star also means that it is likely to be experiencing a runaway greenhouse effect, where increasing temperatures eventually lead to the evaporation of water and the loss of habitable conditions. While Kepler 452b's distance from Earth makes it difficult to study in great detail, its Earth-like qualities and the fact that it orbits a sun-like star make it a crucial point of reference in understanding planetary habitability. Future telescopes may be able to glean more information about this distant exoplanet. In addition, K2-18b is a fascinating super-Earth located 124 light-years away in the constellation Leo. What makes K2-18b so extraordinary is the detection of water vapor in its atmosphere, making it the first exoplanet in the habitable zone with confirmed water vapor. This discovery, made by the Hubble Space Telescope in 2019, immediately positioned K2-18b as one of the most promising candidates for further study. K2-18b is about 2.6 times the size of Earth and 8.6 times its mass, meaning it is likely a mini-Neptune with a thick atmosphere of hydrogen and helium. Despite its gaseous nature, the planet may have a rocky core and liquid water, a combination that intrigues scientists searching for signs of life. The presence of water vapor raises the possibility that liquid water exists on the planet's surface or in its atmosphere. Proxima c, another planet in the Proxima Centauri system, has also captured the attention of astronomers since its discovery in 2020. Unlike Proxima b, Proxima c orbits much farther from its parent star, making it an unlikely candidate for life as we know it. However, its large size, estimated to be about 6 times that of Earth, makes it a compelling object for study. Proxima c may have a thick atmosphere or even rings similar to those of Saturn. While it lies outside the habitable zone, studying this planet could provide valuable information about planetary formation and the dynamics of multi-planet systems. Additionally, Proxima c's proximity to Earth makes it an excellent candidate for future direct imaging missions.
That allows us to see this kind of previously hidden aspect of a galaxy in this amazing detail that was previously inaccessible.
The James Webb Space Telescope continues to deliver astonishing insights into the cosmos, rewriting what we thought we knew about distant stars, galaxies, and even planets beyond our solar system. One of its most captivating recent discoveries is centered on Proxima b, an exoplanet orbiting the closest star to our Sun, Proxima Centauri. This planet, already a subject of significant interest for its potential habitability, has now been observed in unprecedented detail thanks to Webb's powerful infrared vision. Fascinatingly, the new image of Proxima b is not just the clearest ever taken. It also reveals something strange that could change how we perceive this enigmatic world and the search for life beyond Earth. Join us as we dig deep into the latest revelations of Proxima b. The star Proxima Centauri isn't visible to the eye, but it's one of the most noted stars in the heavens. That's because it's part of the Alpha Centauri system, the closest star system to our Sun. Alpha Centauri consists of 3 known stars. Of the 3, Proxima is closest, at 4.2 light-years away. Usually, when stars are so close to Earth, they appear bright in our sky. For example, consider the star Sirius in the constellation Canis Major. Sirius is the brightest star in Earth's sky at just 8.6 light-years away. So why isn't Proxima Centauri at 422 light-years away even brighter? But far from being bright, Proxima is exceedingly dim. It shines at about 11 magnitude. To put that figure in perspective, first you need to know that we have a stellar magnitude scale. According to this scale, the brightest stars in our sky are first magnitude. The Sun and Moon, plus the planets Venus and Jupiter, are much, much brighter than first magnitude. So with a magnitude of plus 11, in visible light, Proxima b is only 0.0056%, as luminous as our Sun. And that's the nature of red dwarf stars like Proxima. These stars, the most common sorts of stars in our Milky Way galaxy, are too puny to shine brightly. Despite its faintness, the discovery of Proxima was no miracle. In fact, the discovery of Proxima b was made using the radial velocity method, which measures the subtle wobbles in a star's motion caused by the gravitational influence of an orbiting planet. This technique allowed researchers to detect the gravitational pull of Proxima b on its host star, revealing the presence of an exoplanet in the habitable zone of Proxima Centauri. Proxima b is believed to be a rocky planet, similar in size to Earth, with a minimum mass about 1.17 times that of Earth. It orbits Proxima Centauri at a distance of approximately 0.05 astronomical units, which is much closer to its star than Mercury is to the Sun. However, due to Proxima Centauri's lower luminosity, this close orbit places Proxima b within its habitable zone. For those who don't know, the habitable zone is where liquid water could theoretically exist, assuming the planet has the right atmospheric conditions. However, several challenges make the question of habitability more complex. One of the key issues with Proxima b is that it is likely tidally locked, meaning one side of the planet always faces its star while the other remains in perpetual darkness. This would create extreme temperature variations between the two hemispheres, with one side possibly being scorched while the other remains frozen. However, scientists have speculated that if Proxima b has an atmosphere, it could help redistribute heat around the planet, potentially allowing for a more temperate climate. In a tidally locked world, the terminator line, the area between the day and night sides, might be where conditions are most conducive to life. This narrow region, which receives some sunlight but not too much, could maintain more moderate temperatures, creating a habitable environment if the right atmospheric conditions exist. On the other hand, Proxima Centauri's frequent stellar flares are one of the most significant obstacles to the habitability of Proxima b. These flares can release powerful bursts of ultraviolet and X-ray radiation, which could erode a planet's atmosphere over time. In 2017, astronomers observed a particularly massive flare from Proxima Centauri, which was estimated to be about 10 times more powerful than any flare ever recorded from our Sun. For Proxima b, which orbits much closer to its star than Earth does to the Sun, such flares could have devastating consequences. At that time, the potential presence of an atmosphere once again became a critical factor in determining the habitability of Proxima b. If the planet has retained a thick enough atmosphere, it could help protect its surface from the harmful effects of stellar flares while maintaining the pressure necessary for liquid water to exist. Without an atmosphere, the planet would be exposed to intense solar radiation and extreme temperatures, making it unlikely that life could thrive. One possible scenario is that Proxima b possesses a thick atmosphere of carbon dioxide, which could create a greenhouse effect, trapping heat and keeping the planet warm enough to support liquid water. However, if the planet has lost its atmosphere due to stellar flares, its surface would be barren and inhospitable. In another case, the planet's magnetic field, if it exists, would play a crucial role in protecting its atmosphere from being stripped away by these flares. Unfortunately, we currently lack detailed information about Proxima B's magnetic field and its ability to shield the planet from stellar radiation. Thus, the prospect of life on Proxima B remains a subject of intense debate. While the planet's location in the habitable zone is promising, the challenges posed by tidal locking and stellar flares complicate the picture. Some scientists argue that life could exist in subsurface oceans, protected from radiation by a thick layer of ice or rock, similar to the proposed habitability of moons like Europa and Enceladus in our solar system. Another possibility is that life on Proxima B, if it exists, could have evolved to withstand high levels of radiation. On Earth, there are extremophils, organisms that thrive in extreme conditions, such as high radiation or intense heat. If similar life forms evolved on Proxima B, they might be capable of surviving the harsh conditions created by Proxima Centauri's flares. With these possibilities, Proxima B stands as a significant milestone in the search for habitable exoplanets and the potential for extraterrestrial life. Its proximity to our solar system, combined with its position within the habitable zone of Proxima Centauri, makes it a key target for scientific investigation. And the James Webb Space Telescope is one of the main instruments that could play a crucial role in the search. Launched in 2021, the Webb telescope is the most advanced space telescope ever built. Unlike its predecessor, the Hubble Space Telescope, which primarily operates in the visible and ultraviolet spectrum, James Webb focuses on infrared light. This allows it to peer through cosmic dust clouds and observe objects in much finer detail. For exoplanets like Proxima B, Webb's infrared vision is especially useful because it can pick up heat signatures, atmospheric compositions, and other vital clues that visible light telescopes might miss. And more than expected, James Webb has truly upended our understanding of the closest exoplanet to Earth by providing a direct glimpse of Proxima B, one that is both breathtaking and baffling. The new image captured by Webb's is the clearest view humanity has ever had of Proxima B. Unlike previous images, which were fuzzy and offered little in the way of surface detail, this new image provides a much sharper view of the exoplanet. We can now discern features on Proxima B's surface that were previously impossible to detect. One of the most significant revelations from this image is the distinct difference in appearance between Proxima B's day side and its night side. The daylight side appears to be brighter than expected, which could indicate the presence of reflective clouds or even ice, while the night side shows faint glows, something astronomers are still puzzling over. Initial theories suggest that this glow could be caused by auroras, much like the northern and southern lights on Earth. Given that Proxima Centauri is a red dwarf star known for its frequent and intense solar flares, it is plausible that these flares are interacting with Proxima B's magnetic field, if the planet has one, to produce the glow. This would imply the presence of an atmosphere capable of conducting solar wind particles, a tantalizing hint that Proxima B might have some form of magnetic shield similar to Earth's. Another possible explanation for the glow is volcanic activity. Some researchers believe that Proxima B may have active volcanoes that could be emitting light on the dark side of the planet. If this is the case, it could indicate a geologically active world, possibly with internal heat sources that could support some form of life below the surface. However, the most exotic theory proposes that the glow might be artificial in origin, a signal of advanced alien technology. While this idea is speculative and not widely accepted by the scientific community, it cannot be entirely ruled out until more data is gathered. On one hand, the reflective nature of the planet's day side suggests the presence of water, ice, or clouds, which are all positive indicators for life. If Proxima b has an atmosphere capable of distributing heat around the planet, it could mitigate the temperature extremes caused by tidal locking, creating a more temperate zone where life might thrive. On the other hand, Proxima Centauri's frequent solar flares pose a significant challenge for life on Proxima b. These flares bombard the planet with high levels of radiation, which could strip away the atmosphere over time, leaving the surface barren and inhospitable. However, the presence of auroras or a magnetic field, as suggested by the glow on the night side, could indicate that Proxima b has some defense against this radiation. Moreover, the potential volcanic activity raises the possibility of subsurface life. If there are active volcanoes on Proxima b, they could create environments similar to hydrothermal vents on Earth, where life thrives in complete darkness, feeding off the chemical energy released by the planet's interior. In this scenario, life on Proxima b might exist not on the surface, but deep below it, protected from the harsh radiation of space. After all, the image of Proxima b captured by James Webb is a game changer, not only because of the new details it provides, but also because it opens up a host of new questions. Is Proxima b truly habitable, or is it a hostile world with only a few tantalizing signs of potential life? Could the strange glow on its night side be a natural phenomenon, or is it evidence of something more unusual, perhaps even artificial? Future observations will be critical in answering these questions. James Webb will continue to monitor Proxima b, focusing on its atmospheric composition, temperature variations, and potential signs of life. In addition, ground-based observatories, such as the upcoming Extremely Large Telescope, will provide even more detailed follow-up observations. Meanwhile, missions like Breakthrough Starshot, which aims to send tiny, high-speed spacecraft to the Alpha Centauri system, could provide a closer look at Proxima b within our lifetimes. Breakthrough Starshot is part of the larger Breakthrough Initiatives, a series of space-related projects aimed at answering some of humanity's most profound questions, including whether life exists beyond Earth. Announced in 2016, the Starshot initiative set its sights on reaching another star within a single generation. The project has one goal: to send a fleet of tiny, lightweight spacecraft, known as starships, on a journey to Proxima b at approximately 20% the speed of light. At this velocity, the spacecraft could complete the 4.24 light-year journey in just over 20 years, allowing us to explore this alien world in unprecedented detail. And to do that, we need groundbreaking technology. As told, instead of massive spacecraft, which would require enormous amounts of energy to accelerate to a fraction of the speed of light, the mission plans to send tiny probes no larger than a postage stamp, each weighing just a few grams. These starships would be attached to lightweight, ultra-thin sails made from materials like graphene or metamaterials. Using lasers on Earth, an array of high-powered beams would propel these sails to extraordinary speeds, bypassing the traditional limitations of chemical propulsion. The key technology driving the Breakthrough Starshot mission is a concept known as photon propulsion. Light carries momentum, and when photons strike a surface, they impart a tiny push. While the force from individual photons is minuscule, concentrated beams of light, such as those generated by a laser, can exert a powerful force over large distances. This is the foundation of Starshot's proposed propulsion system. A powerful ground-based laser array, known as a light beamer, would fire concentrated beams at the starship's sails, propelling them to speeds of up to 100 million kilometers per hour, or about 20% of the speed of light. This propulsion system is elegant because it relies on no fuel carried by the spacecraft itself, allowing for an extremely lightweight design. The sails, each about 4 meters wide, would be designed to catch the light and use it to accelerate the starships. Once in space, the light beam would continuously push on the sail, accelerating the spacecraft to relativistic speeds within minutes. One of the major engineering challenges is maintaining precision over such long distances. The laser array would need to focus on a tiny object millions of kilometers away with an incredible degree of accuracy. Additionally, the star chips must be equipped with tiny but powerful electronics capable of sending data back to Earth across light years of space. They must also survive the extreme environment of space, including the hazards of radiation and interstellar dust. The Breakthrough Starshot mission is divided into several key phases. The first phase involves the development of the necessary technology, particularly the light beamer laser array and the star chips. While the basic principles of photon propulsion have been tested on Earth, scaling them to the level needed for interstellar travel presents a host of technical challenges. Once the technology is ready, the next phase will involve testing the star chips in Earth orbit to ensure they can survive the harsh conditions of space. These tests will help refine the design and ensure that the systems can operate autonomously over long distances. The final phase, launching the fleet of star chips, would see hundreds, if not thousands, of these tiny spacecraft released into space. They would travel in a swarm, increasing the chances that at least a few will make it to Proxima b and return data to Earth. After the star chips are launched, they would begin their long journey toward Proxima Centauri. Although the journey would take over 2 decades, the probes themselves would be traveling faster than any spacecraft ever built by humans. Along the way, they might also collect valuable data on the interstellar medium, the space between stars, which is still largely a mystery to scientists. The ultimate goal of Breakthrough Starshot is to send back images and data from Proxima b. While the star chips are too small to carry large instruments, they will be equipped with miniature cameras, sensors, and communication devices. Upon arrival at Proxima b, the spacecraft would snap high-resolution images of the planet's surface and atmosphere, providing the first-ever close-up views of another potentially habitable world. Another ambitious concept for reaching Proxima b is Project Lyra, spearheaded by the Initiative for Interstellar Studies. Unlike Breakthrough Starshot, which aims for extreme speed using lightweight probes, Project Lyra is focused on developing a mission that could send larger spacecraft, albeit at slower speeds. The project's goal is to develop a probe that could be launched with current or near-future space propulsion technologies, such as nuclear-powered engines or solar sails, and would take longer to reach Proxima b, potentially several centuries. While this timeline seems long compared to Starshot, Project Lyra would allow for a much more sophisticated payload, enabling the probe to perform unprecedented detailed studies of Proxima b upon arrival. While telescopes like the James Webb Space Telescope and ground-based observatories will continue to provide valuable data, nothing compares to the ability to directly observe and measure conditions on or around an exoplanet. The scientific goals of the mission are numerous. Search for signs of life. The most tantalizing goal of Project Lyra is to search for biosignatures, chemical signs that life may exist or have existed on Proxima b. This could include the detection of gases like oxygen, methane, or other organic compounds in the planet's atmosphere. Characterize the atmosphere. Understanding the composition, structure, and dynamics of Proxima b's atmosphere is crucial for determining its habitability. A detailed analysis could reveal whether the planet has an atmosphere similar to Earth's, or if it is more like Venus, with a thick, hostile environment. Study the surface. Another key goal is to study the planet's surface. Does Proxima b have oceans, continents, or vast desert landscapes? Is there volcanic activity or other geologic processes? High-resolution imaging could provide the answers. Understand Proxima Centauri's influence. Proxima Centauri is a red dwarf star, and red dwarfs are known for their violent stellar flares. Understanding how these flares impact Proxima b's atmosphere and surface is critical for assessing its habitability. Examine Proxima Centauri's system. In addition to Proxima b, there could be other, smaller planets in the Proxima Centauri system. Project Lyra could study these objects as well, providing a more comprehensive picture of our nearest stellar neighbor. To achieve these scientific goals, the Project Lyra team must overcome a series of formidable technological hurdles. Interstellar travel is unlike any mission humanity has ever attempted, and success will require pushing the boundaries of current space exploration technology. The single most significant challenge for Project Lyra is the propulsion system. Current rocket technology, which relies on chemical propulsion, is far too slow for interstellar travel. As a result, the Initiative for Interstellar Studies has been investigating alternative propulsion methods that could accelerate a spacecraft to a significant fraction of the speed of light. One of the most promising ideas is to use a laser sail propulsion system, similar to the concept being explored by the Breakthrough Starshot Initiative. In this approach, a spacecraft equipped with a lightweight reflective sail would be propelled by powerful lasers fired from Earth. These lasers would push the sail, accelerating the spacecraft to speeds of up to 20% of the speed of light. At such speeds, a spacecraft could reach Proxima Centauri in about 20 years. Another propulsion concept involves nuclear fusion. Fusion-powered spacecraft could, in theory, achieve much higher speeds than chemical rockets, though fusion technology is still in its early stages of development. Building a spacecraft capable of withstanding the rigors of interstellar travel is another monumental challenge. The spacecraft will need to be highly efficient, lightweight, and durable enough to survive decades in the harsh environment of deep space. The design of the spacecraft's instrumentation is equally critical. It must be equipped with cutting-edge sensors, cameras, and communication systems capable of transmitting data back to Earth from over 4 light-years away. This will require breakthroughs in both miniaturization and power generation, as the spacecraft will have to operate independently for decades without any external sources of power. Navigating a spacecraft to a destination 4.24 light-years away is an immense challenge. The spacecraft will need to be equipped with advanced autonomous navigation systems to adjust its course as it travels through interstellar space. It will also need to avoid collisions with interstellar dust and other hazards. Communicating with Earth from such a vast distance is equally daunting. Even at the speed of light, signals from Proxima Centauri would take over 4 years to reach Earth, meaning that real-time communication is impossible. The spacecraft will need to be highly autonomous, capable of making critical decisions without input from mission control. Project Lyra's timeline is divided into several phases, each of which presents unique challenges and objectives. Phase 1. Feasibility Studies. The initial phase of the mission involves conducting feasibility studies to determine the best approach for interstellar travel. During this phase, the Initiative for Interstellar Studies team will explore various propulsion systems, spacecraft designs, and mission architectures to identify the most viable options. This phase also involves simulations and modeling to estimate the potential performance of different propulsion systems. Phase 2. Technology Development. Once a feasible mission architecture has been identified, the next phase will involve developing the necessary technologies. This includes building and testing propulsion systems, spacecraft components, and communication systems. Given the unprecedented nature of interstellar travel, this phase is expected to take several years, if not decades. Phase 3. Launch. If all goes according to plan, the spacecraft could be ready for launch by the mid-21st century. The exact launch date will depend on the progress of technology development and funding. Once launched, the spacecraft will begin its long journey to Proxima Centauri, gradually accelerating to a significant fraction of the speed of light. Phase 4. Arrival and data transmission. After traveling for about 20 years, the spacecraft will reach the Proxima Centauri system. It will then spend several months or years studying Proxima b and its environment before transmitting its data back to Earth. Given the 4-year communication delay, It may take decades after the spacecraft's arrival for scientists on Earth to receive the full dataset. In short, Project Lyra represents a bold leap into the unknown, with profound implications for our understanding of the universe and our place within it. If successful, it could provide humanity with its first direct observations of an exoplanet, and potentially even evidence of extraterrestrial life. The mission also has the potential to inspire new generations of scientists, engineers, and explorers to push the boundaries of what is possible. Moreover, the technologies developed for Project Lyra could have far-reaching applications beyond interstellar travel. Advances in propulsion, miniaturization, and autonomous systems could revolutionize space exploration closer to home, making it easier to explore the outer planets, moons, and asteroids of our own solar system. A worth note, while biosignatures remain crucial in the quest to find life, the search for technosignatures opens up new frontiers. They refer to detectable signs of technology that could suggest the existence of intelligent extraterrestrial beings. Technosignatures can take many forms, each offering a different avenue for the potential detection of advanced extraterrestrial life. Below are some of the key technosignatures scientists are actively searching for. 1. Radio signals. Radio signals have long been the primary focus of SETI, or Search for Extraterrestrial Intelligence efforts. The idea is simple. A technologically advanced civilization would likely use radio waves for communication, just as we do on Earth. Radio waves can travel vast distances across space without significant interference, making them ideal for interstellar communication. However, detecting these signals presents numerous challenges. First, the universe itself is filled with natural radio emissions from stars, planets, and black holes, so distinguishing between a naturally occurring radio wave and one created by an alien civilization is incredibly difficult. Second, we would need to tune in at the right frequency. An advanced civilization might be using wavelengths or forms of communication that we haven't even considered. Despite these challenges, the search for radio signals continues to be a central part of SETI. Projects like Breakthrough Listen, a $100 million initiative launched in 2015, are using some of the world's most advanced radio telescopes to scan the skies for any artificial signals. 2. Lasers and optical signals. Another potential technosignature is laser emissions. Lasers are highly focused beams of light that can travel great distances without losing much of their intensity. A technologically advanced civilization could use lasers to communicate or signal their presence. The advantage of lasers is that they could be highly directional, making them easy to detect if aimed directly at Earth. However, the narrowness of laser beams also makes them difficult to observe unless the beam happens to be pointed at us. Detecting a laser signal would require sophisticated optical telescopes and a lot of luck. Nevertheless, efforts are underway to search for laser signals. Some scientists are developing techniques to scan large portions of the sky in search of these concentrated beams of light. 3. Megastructures, Dyson spheres, and stellar engineering. Perhaps one of the most intriguing types of technosignatures is the potential for megastructures built by advanced civilizations. One of the most famous theoretical megastructures is the Dyson sphere, a concept proposed by physicist Freeman Dyson in the 1960s. A Dyson sphere would be a massive structure built around a star to capture nearly all of its energy output, providing a civilization with virtually limitless energy. Detecting a Dyson sphere would be possible by observing a star whose light is partially or completely blocked by such a structure. This idea gained popular attention in 2015 when astronomers observed unusual light fluctuations around Tabby's star, leading some to speculate about the presence of a megastructure. However, subsequent studies have suggested that the dimming could be caused by natural phenomena such as dust clouds. Beyond Dyson spheres, other forms of stellar engineering could leave detectable signatures. For example, a civilization could manipulate the orbits of planets or construct large-scale habitats in space, any of which might produce unusual light patterns or gravitational effects. 4. Waste heat and infrared emissions. An advanced civilization using vast amounts of energy would inevitably produce waste heat as a byproduct. This waste heat would be detectable in the form of infrared radiation, which is emitted by objects as they lose heat. In theory, a civilization using a Dyson sphere or other massive energy-gathering structures would produce a detectable amount of waste heat. Astronomers are actively searching for unusual infrared signatures that might indicate the presence of advanced technology. Natural objects, such as stars and galaxies, also emit infrared radiation, so any detection would have to be carefully analyzed to rule out non-technological sources. 5. Artificial light. On Earth, cities and industrial activity produce artificial light that can be seen from space. It stands to reason that an advanced extraterrestrial civilization might also produce artificial light, especially on the night side of its home planet. Observing artificial light on the dark side of an exoplanet could provide a compelling techno-signature of a technological society. This concept is particularly appealing because it doesn't require advanced knowledge of alien communication methods. Instead, it relies on the assumption that intelligent beings, like humans, would manipulate their environment to produce light, which could then be detected by telescopes. The search for techno-signatures is a multidisciplinary effort, combining astronomy, computer science, engineering, and physics. Breakthrough. Listen is one of the most prominent initiatives currently scanning the skies for techno-signatures, particularly in the form of radio waves. It has gathered an enormous amount of data, which is being analyzed by powerful computers using machine learning algorithms to detect any unusual patterns that might indicate an artificial signal. Another effort in the search for techno-signatures is the use of space-based observatories. For example, the James Webb Space Telescope is helping in the search for potential techno-signatures by analyzing the atmospheres of distant exoplanets. Unusual chemical compositions that cannot be easily explained by natural processes might point to the presence of technological activity. Finding a techno-signature would be one of the most profound discoveries in human history. It would mean that we are not alone in the universe and that other civilizations have not only emerged but also developed advanced technologies. The implications of such a discovery would be staggering. It could force us to rethink our place in the cosmos and perhaps provide us with insights into the future trajectory of our own civilization. If we were to detect a techno-signature from a civilization much older and more advanced than ours, we could learn about technologies that might one day be within our grasp. It could also offer us hope that advanced civilizations can survive long-term challenges such as resource depletion, climate change, and even cosmic catastrophes. On the other hand, the absence of techno-signatures could suggest that technological civilizations are either incredibly rare or short-lived, raising important questions about the long-term sustainability of technology-driven societies. In huge news for astronomy fans, James Webb may have made an intriguing breakthrough in the field of space exploration. The Supreme Observatory has just made a groundbreaking discovery light years outside our solar system, when capturing city lights 7 trillion miles away from Earth. This remarkable finding then sparked curiosity about the possibility of extraterrestrial life. But after all, has James Webb really found life beyond Earth? Join us as we dig deep into Webb's stunning discovery that could blow your mind. In January 1992, 2 radio astronomers announced a discovery that would change our view of the universe forever. Alexander Wolszczan had been scanning the skies to study a type of spinning star known as a pulsar, but something was blocking his view. Curiosity piqued, Wolszczan eventually discovered the root of the interference: 2 planets in orbit around the star. Fellow radio astronomer Dale Frail verified the data, and the pair made their incredible announcement to the world. They had discovered the first ever known extrasolar planets, or exoplanets. The existence of exoplanets, planets orbiting stars other than our Sun, had long been theorized, but now there was definitive proof. For the first time, humanity could be sure that the solar system in which it lived was not alone. There were planetary systems out there in the cosmos. Since this discovery, there has been a concerted effort by astronomers to find even more of these exoplanets. At last, through a combination of strong instruments like NASA's Kepler Space Telescope, we've surpassed 5,000 known exoplanets. As is often the case, these discoveries have been tremendous and have answered some of our deepest questions about the cosmos. Nevertheless, even deeper ones now remain. That's why now, a new generation of exoplanet hunting missions is conducting for follow-up investigations to build on Kepler's progress and make discoveries that could change what we know about how planets form and how life might arise elsewhere in the universe. Perhaps most exciting is the James Webb Space Telescope. James Webb is seen by many as the successor to the Hubble Space Telescope, albeit 100 times as powerful, and rather than orbiting Earth, will instead orbit the Sun at a distance of 1.5 million kilometers from our planet. This helps it avoid heat from the Sun, Earth, and the Moon, and remain cool, around minus 225 degrees C. Why? Because warm objects emit infrared light, and infrared is the primary method of Webb to observe the universe. One of its goals will be to observe young planets forming around young stars. Stellar formation begins when clouds of gas and dust in space begin to clump mass together, growing so big that they eventually collapse under their own gravity. What remains is a young protostar surrounded by a spinning disk of dust. Out of this dust may form a system of planets orbiting the central star, just like our own solar system. In optical light, these still-forming planets are obscured by the dust, but infrared can peer through it to get an unprecedented look at planetary formation in action. As Dr. Jane Rigby, one of the mission's project scientists, said, "We build space telescopes because they can take sharper pictures, due to the fact that Earth's atmosphere is not in the way distorting what we're trying to see. If we want to study most colors of infrared light, then we need to go into space because that light cannot shine through our atmosphere." What's really exciting is Webb's ability to split starlight, a technique known as spectroscopy. By splitting the starlight that has passed through the atmosphere of an exoplanet, scientists can analyze the chemical signatures hidden within and learn much about the properties of that exoplanet, whether it has a lot of water vapor in it or other chemicals that might reveal something about the processes occurring on its surface. In the word of Rigby, this is our first chance to understand in detail the atmospheres of exoplanets, and there's a lot of interest in studying rocky planets like our own. And just as expected, more than 2 years after operation, astronomers are using the telescope to look for life on thousands of newly discovered planets. There is a distant world where quartz crystals float above a searing, hot, puffy atmosphere. Vaporized sand grains, not water droplets, form the clouds that fill the sky on WASP 107b, a planet 1,300 light-years from Earth. Then there is GJ1214, the sauna planet. With a mass 8 times that of Earth, it orbits its parent star at a distance that is 1/70th of the gap between Earth and the Sun and seems to be coated in a thick, dense atmosphere containing vast amounts of steam. Or there are the giant, Jupiter-sized planets of the Orion Nebula, which have been discovered free-floating in space, rogue worlds that appear to be unconnected to any parent star, to the bafflement of astronomers. These strange, remote planets could not be more diverse or dramatically different from each other, although they do share one common feature. Their wonders are now being revealed by the James Webb Space Telescope. Of course, those discoveries are just the tip of the celestial iceberg. Crucially, several hundred are relatively close to Earth, and these are now ripe for study with the James Webb. One of them is Proxima Centauri, the closest star to our Sun. We've carefully observed it for both radial velocity and transiting imperfections, looking for any sign of a planet around it. Proxima Centauri is a tiny, low-mass red dwarf star, emitting just 0.17% the radiation of the Sun. There are many ways that the star is different from ours, being smaller, cooler, flaring far more often, and the fact that it will live not for billions of years, like our Sun, but for trillions. Proxima Centauri is also part of a trinary system, where the two main components, Alpha Centauri A and B, are roughly Sun-sized and orbit one another relatively close by, but Proxima Centauri is much lower in mass, cooler, and more distant. When we observe Proxima Centauri, we don't see any evidence for a transiting world, and any planets that are there are far too dim to be seen with direct imaging and our current technology. But we do see the signatures from radial velocity of a single, massive world that orbits it. From the observations we've made, we can determine the following properties of this planet, now known as Proxima b. It has an orbital period of 11.2 days. The amount of starlight it receives from Proxima Centauri, 65% of what we get here, should give it Earth-like temperatures if it has an Earth-like atmosphere. It has a minimum mass that's 130% the mass of Earth, just a little more massive than our planet. There may be other planets present as well, either lower in mass and/or with much longer orbital periods, which our observations are not yet sensitive to. But this one, at least, is real. But what is it like? Is it Earth-like? There are many ways we know that it must differ from our planet Earth, including it must be tidally locked to its star, where the same face always faces the star and the same face always faces away. It will have 3 climate zones, an ultra-hot one where it's always sunny, an ultra-cold one where it's always night, and an on-the-border one where it's always sunset, sunrise, and the solar flares coming from the star will potentially be a danger for stripping the atmosphere away. We can, of course, concoct scenarios where the planet hangs onto or replenishes its atmosphere and has conditions conducive to life. But this is nothing more than wishful thinking. In reality, we do not even know whether this planet is Earth-like or Neptune-like. The typical border between an Earth-like world, where you have a rocky surface with a thin atmosphere, and a Neptune-like world, where you have a large gas envelope surrounding your world, is about 2 Earth masses. Proxima b has a minimum mass of about 1.3 Earths, but that's if the alignment is perfectly edge-on. Since there's no transit, we know the alignment cannot be exactly perfect, but how imperfect is it? That's gloriously unknown. If the alignment is inclined at more than about 25 degrees from our line of sight, it's likely to be a gaseous world, not a rocky, Earth-like one. But at this point, without further information, we cannot know. If we were going to be as accurate as possible, we would state that there is a planet with an orbital period of 11.2 days orbiting the closest star to us, Proxima Centauri. It receives 65% of the solar energy that Earth receives and has a minimum mass of 130% the mass of Earth. That's it. That's all we know for certain. If we wanted to speculate, we could discuss all the reasons Proxima b is likely to be inhospitable to life, what challenges this planet faces if it wants to achieve habitability, and what we'd have to measure to know for sure. But the truth is that we don't know any more than this. Until James Webb has better, more comprehensive data on this world, all we know is its period, the energy it receives, and its minimum mass. The age of exoplanet astronomy is upon us, but it's still in its infancy in many ways. Wonder about the possibilities and feel free to speculate as to what might be out there, but never conflate your hopes with what's actually likely. The only way to know for sure is to build the right instruments and observatories and take the critical data. The only way to know what's out there for certain is to find out for ourselves. And as told, Proxima b is not the only exoplanet that caught James Webb's eyes. In a previous finding, the observatory centered on a world known as K2-18b, a planet orbiting a faint red star some 120 light-years from Earth. Data from Hubble and James Webb show a giant planet, roughly 8 times the size of Earth, but one that seems to have an atmosphere rich in hydrogen and a surface covered in deep oceans. More intriguing, data published last year claimed the Webb telescope had found evidence of dimethyl sulfide in K2-18b's atmosphere. On Earth, this chemical is a certain sign of life, and so, to find it floating through the air of a distant planet is interesting, to say the least. Add that to earlier speculation that K2-18b is a Hyson world, a hypothetical type of planet that could be habitable, and you have all the ingredients for a groundbreaking claim of alien life. Still, caution is to be advised. No Hysian world has ever been definitively found, and some argue that they do not really exist at all. Even if they do, it is not certain K2-18b is one. And the signature of dimethyl sulfide was weak, so weak, in fact, that it might not be there at all. 3 questions, then, surround this world. Is it really a Hysian world? Is dimethyl sulfide really present in its atmosphere? And if it is, does that definitely imply the presence of life? Those are hard questions to answer, and what answers exist is often controversial. Thus, to solve the riddles, we need more data. That could come from the James Webb, which might be capable of better resolving the signal with more time. But it may need to wait for the next generation of telescopes, some of which will be designed to sniff out such chemicals with much greater precision. Either way, it is still too early to settle the question of dimethyl sulfide. Regardless, one thing can't be denied. The Webb Space Telescope now is the largest, most powerful, and most complex telescope ever launched into space, and its results have surpassed all our expectations. In a recent observation, the Webb telescope has performed a weather report for a distant planet. The powerful space telescope forecasts extreme wind speeds, blisteringly hot temperatures, and blankets of rock clouds for the world, named WASP-43b. As such, the extrasolar planet, or exoplanet, demonstrates just how strange alien planets outside the solar system can be. WASP-43b orbits a star located around 283 light-years from Earth. It sits so close to its star, in fact, that it completes an orbit in just around 19 Earth hours. This proximity, equal to around just 1.3 million miles, 2.1 million kilometers, means the planet, with a mass around 1.8 times that of Jupiter and a width 0.9 times that of the gas giant, is tidally locked to its star, WASP-43. Thus, one side of WASP-43b, its day side, permanently faces the star and is constantly bombarded by radiation, sending planetary temperatures soaring to around 1250 degrees Celsius. That's hot enough to melt lead. The other side of the planet, its night side, faces permanently out into space, resulting in temperatures falling to a relatively chilly 600 degrees Celsius. These qualities mean WASP-43b is classified as a hot Jupiter planet. The James Webb Space Telescope, transiting exoplanet early release science team, was able to use the telescope's MIRI to classify the climate of WASP-43b and the type of weather it experiences on its day and night sides. As team member Laura Kreidberg, director at the Max Planck Institute for Astronomy, said in a statement, "With the new observing power of JWST, WASP-43b has been unveiled in unprecedented detail. We see a complex, inhospitable world with furious winds, massive temperature changes, and patchy clouds likely made of rock droplets. WASP-43b is a reminder of the vast range of climates that are possible on exoplanets and the many ways in which Earth is special. WASP-43b was discovered in 2011 because of a dip in the light scientists saw exhibited by WASP-43. This dip occurred as the planet crossed between the face of its star and Earth from our perspective. During the transit, Scientists also saw that infrared light the planet emits in response to starlight varied. The main result of Webb's investigation of WASP-43b was thanks to this infrared light variation observed between the day side and the night side of the exoplanet as it orbited its star. The variations, more particularly, helped scientists build a map that shows how temperatures are distributed across the entire hot Jupiter. Ultimately, the team found the variation in temperature between day and night sides of WASP-43b is too great to be seen in an atmosphere bereft of cloud cover. However, any possible clouds above WASP-43b's surface are not likely to be water-based, like those enshrouding Earth. They wouldn't even be ammonia clouds like those we see around Jupiter. WASP-43b is just too hot for either. Rather, this world's clouds might be made of rock. Vaporized material, such as rock, is carried from the day side to the night side of WASP-43b by powerful winds reaching speeds of 5,600 miles per hour, 9,000 kilometers per hour. That's 3.5 times as fast as the top speed of a jet fighter here on Earth. Then, once on the night side of the planet, scientists believe this material cools and condenses. This means the thick cloud cover on the night side of WASP-43b is likely composed of droplets of liquid rock that had vaporized on the planet's day side. To that end, the researchers found that the day side of WASP-43b appears to be cloudless. To determine the composition of WASP-43b's atmosphere, the team split the observed infrared light into separate wavelengths, thus creating what's known as a spectra. Because chemicals and elements absorb and emit light at characteristic wavelengths, they leave behind fingerprints in such spectra. As Taylor Bell, team leader and a scientist with NASA's Ames Research Center, said in the statement, "With Hubble, we could clearly see that there is water vapor on the day side. Both Hubble and Spitzer suggested there might be clouds on the night side, but we needed more precise measurements from James Webb to really begin mapping the temperature, cloud cover, winds, and more detailed atmospheric composition all the way around the planet." Not only did James Webb's investigation determine that water vapor is found all over WASP-43b on both its hot and cooler sides, but it allowed the scientists to see a lack of methane in the planet's atmosphere. Hot Jupiters are normally expected to produce water and methane on their night sides via reactions between hydrogen and carbon monoxide. The team thinks WASP-43b lacks methane because its raging winds pass these reacting molecules through the night side of the planet too fast for the molecules to react with anything and create methane in detectable amounts. Any small amount of methane that is created would probably mix with other gases and quickly get carried to the planet's day side, where intense heat destroys it. James Webb isn't done with WASP-43b just yet. A separate team is currently using the $10 billion telescope's NIR SPEC instrument to perform a follow-up study of the planet. Not only should this improve the MIRI temperature map, but these observations should also lead to measurements of gaseous carbon monoxide in the atmosphere of WASP-43b, providing a better overall picture of this extreme world's chemical composition. In a recent eye-catching observation, the James Webb Space Telescope has captured incredibly sharp images of the Horsehead Nebula, one of the most iconic celestial bodies in the sky over Earth. The Horsehead Nebula, also known as Barnard 33, is a collapsing cloud of dense, cool gas that is illuminated by a hot young star embedded in its top left edge. The horse-like structure that makes this nebula so distinctive has been created because lighter gas has been eroded. This has left a thick pillar of dense gas and dust that is harder to erode. This won't last forever, though. Scientists estimate that in around 5 million years, even this pillar of denser matter will be gone. And as the most powerful telescope ever placed into orbit around our planet, the Webb telescope was able to see details of the Horsehead Nebula that had never before been revealed, showing some regions in a completely new light. The new images show the Horsehead Nebula as turbulent waves of gas rising from the western side of Orion B, a star-forming molecular cloud located 1,300 light-years from Earth in the constellation of Orion. And as a worth note, the Space Telescope Science Institute has announced which astronomy proposals have been selected to be given time with the James Webb Space Telescope over the next 2 years. One of the teams lucky enough to get time with James Webb during Cycle 3 will be searching for moons outside the solar system. These are known as extrasolar moons, or simply exomoons. Thus far, exomoons have proved an elusive subject for astronomers because they are hunted using the same light-blocking technique employed to spot exoplanets around stars. However, this technique is difficult enough when looking for large worlds beyond Earth. Searching for little exomoons with it is immensely challenging. Not only would exomoons block far less light than the exoplanets they orbit would, but they'd also need to be in the right position at the right time. An exomoon that's detectable would have to be orbiting its planet precisely as that planet's crosses, or transits, the face of its parent star, to obscure some light when viewed from our vantage point in the cosmos. That obstruction would be detected by scientists' equipment, which would allow them to reverse calculate that an exoplanet, or potentially exomoon, gave rise to it. David Kipping, an assistant professor of astronomy at Columbia University, is part of the team that hopes to find moons around the exoplanet Kepler 167e in particular. This gas giant is around the size and mass of Jupiter and is located 1,115 light-years from Earth. In the words of Kipping, Kepler 167e is the best target we've ever had for moon hunting. So, he is hoping that, by focusing on Kepler 167e with Webb's near-infrared imager and slitless spectrograph, he and his team can make the first undisputed detection of an exomoon. This is hopefully just the beginning of the exomoon revolution, new worlds that will surely hold some remarkable secrets, Kipping said. Of course, Webb's Cycle 3 GO projects also include a wealth of investigations focusing on exoplanets themselves and not just their potential moons. This includes a few that wish to determine whether some exoplanets have the conditions needed to support life as we know it. Among those exoplanet habitability projects is one called Constraining the Atmosphere of the Terrestrial Exoplanet, TOI 4481b. This will use Webb's MIRI for 16 hours to determine if a roughly Jupiter-mass exoplanet, which orbits a star around half as massive as the Sun that sits some 39 light-years away, has been able to hang on to its atmosphere. The result could serve as a first step in understanding the habitability of rocky planets and establishing whether M-type stars, also known as red dwarfs, have terrestrial planets with significant atmospheres. This is important in the search for life beyond Earth, because red dwarfs are the most common stars in the Milky Way. In addition, astronomers widely believe the majority of our universe's large galaxies have supermassive black holes in their hearts with masses as great as millions or even billions of suns. Some of these supermassive black holes are actively swallowing gas and dust that surrounds them in disks of matter, called accretion disks. These monster black holes' gravitational influences are thought to heat the material in those accretion disks, causing them to emit bright radiation across the electromagnetic spectrum and create regions called active galactic nuclei, AGN. Additionally, any matter that isn't swallowed by the black hole can be channeled to its poles, where it is blasted out as jets of particles traveling at speeds approaching light. When that happens, the phenomenon is called a quasar. The violent conditions of these events make AGNs and quasars the brightest objects in the universe, often luminous enough to outshine the combined light of every star in the galaxies around them. Our theoretical understanding of supermassive black holes has burgeoned since the Event Horizon Telescope, EHT, revealed the first image of a black hole, the supermassive black hole at the heart of the galaxy Messier 87, M87, in 2019. And James Webb's Cycle 3 missions will further contribute to this knowledge. The Cycle 3 supermassive black hole observation programs include the investigation of quasars in the early universe and the nature of the first black holes. Scientists hope to understand how those black holes may have influenced the growth of galaxies over billions of years. Webb's observations of supermassive black holes in the early universe could also reveal how these cosmic titans grew to the tremendous masses scientists observe before the universe was even 1 billion years old. Such a question can be answered by using MIRI to investigate if a giant molecular cloud that existed around 13.2 billion years ago could have directly collapsed, birthing a heavy black hole seed that would account for a rapid growth mechanism. On the other hand, one of the primary roles of the James Webb Telescope is investigating objects in the early universe. The powerful space telescope has this capacity because the expansion of the universe stretches wavelengths of light from distant objects as this light travels toward us, moving the wavelengths toward the red end of the electromagnetic spectrum. The longer that light has traveled to reach us, the more red-shifted the light has become. This means light that has been traveling for around 12 billion years is extremely red-shifted, all the way into the infrared region of the electromagnetic spectrum and outside the visible range we can see with the unaided eye. Effectively, infrared light is invisible to us. However, the observatory is capable of observing this infrared light and thus helps to investigate the first stars and earliest galaxies, something it will continue to do in 2025 with several Cycle 3 GEO projects. That's why cosmologists particularly enthusiastic about GO projects that will look at an era of cosmic evolution called the Epoch of Rionization, which occurred around 500 million years after the Big Bang. During this period, neutral atoms of hydrogen populating the cosmos were ionized by radiation that stripped away their electrons and left them as ionized hydrogen, or hydrogen ions. Studying high redshift galaxies can reveal more about this crucial stage in cosmic evolution, including how the first galaxies acted as the source of this ionizing radiation. Some of the proposals that catch their interest are understanding galaxy formation at cosmic dawn, galactic winds in the early universe, and dead or alive, unveiling the nature of massive galaxies in the early universe. All of these accepted projects seek to identify and characterize galaxies that are the drivers of the epoch of Rionization. Of course, this is just the tip of the celestial iceberg when it comes to the range of topics Cycle 3 GO projects will cover. Between 2024 and 2025, astronomers will also train telescopes on distant stars to better understand stellar physics and populations, as well as examine the gas that exists between stars that can become the building blocks of the next generation of stars and planets. And though the Webb telescope was designed with the study of distant objects in mind, Cycle 3 will also see the observatory used to study bodies within our own solar system. These will include hunting for the source of gas plumes coming from Saturn's moon Enceladus, investigating the dynamics of the Uranus's rings, and characterizing icy objects that exist in the Kuiper belt at the very edge of the solar system. Looking beyond James Webb Cycle 3, the call for Cycle 4 GO proposals will go out on August 1, 2024, with a deadline set for October 16 this year. The Cycle 4 Telescope Allocation Committee review will run between February 3 and February 12, 2025, with selections revealed around March 5 next year. Webb's Cycle 4 GO programs will then begin making observations of the cosmos on July 1, 2025. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching,